idea of storing information has been around a long time. The invention of a movable type press enabled the mass production of stored information on paper. This historic capability produced fundamental changes in the way people viewed the world. The graduation of information storage from paper means to electronic means spurred a new era, the information age. The advent of the personal computer and new printer technology brought new dynamic power to information processing. The ability to store, recall, manipulate, and print numerical and text information. Like the technological growth in information processing, oscilloscope design began with basic features and grew into the world of digital processing. When first introduced, analog oscilloscopes offered views of electronic events never seen before. And as technology changed, various methods became available to store signals displayed on analog scopes. The introduction of Polaroid land cameras that could be attached to the oscilloscope meant that photographic records could be made of displayed signals. Other advances produced the CRT storage tube, which allowed oscilloscope users to store signals directly on the oscilloscope screen. On a parallel path to CRT storage, advances in digital technology increased computer power while hardware shrunk, making information processing power available for equipment that previously did not have such capability. The desire to unite this processing power with the flexibility of analog scopes prompted companies like Tektronix to produce digital storage oscilloscopes. Digital storage oscilloscopes represent electrical signals with numbers, which lets users capture and store an electrical event, then manipulate it to obtain better information. The methods for digitizing signal information, the terminology, and the typical features of digital storage oscilloscopes are the subjects of this program. A digital storage oscilloscope, or DSO for short, can be broken down into functional blocks. An input amplifier similar to those used in analog scopes, the vertical section, which includes an analog to digital converter that changes the analog signal into numbers, a microprocessor that controls scope functions, a memory for storing the signal numbers, and an output digital to analog converter, which reconverts the signal numbers into analog signals for the vertical output amplifier. An analog trigger block triggers the horizontal section, which includes a precise digital time base, and a digital to analog converter, which changes the time base output to an analog signal. This signal, in turn, drives the analog horizontal output amplifier. Many DSOs use display systems similar to those used in analog scopes, typically consisting of vertical and horizontal output amplifiers, an intensity amplifier, and a cathode ray tube. Other DSOs use vertical raster scan displays. The most important difference between a digital storage oscilloscope and an analog oscilloscope is that a digital scope changes analog signals into numbers. This process is called analog to digital conversion, or A to D for short. To display the stored numbers, the reverse process, called D to A conversion, translates these numbers back into the electrical signals required to produce a display. Once a signal has been converted to numerical data, the values are stored in a memory. This information can be output to a display for immediate viewing, stored in another internal memory, or transferred to an external device. This could include devices such as a disk drive for long-term storage, a computer for more information processing, a hard copy device like a plotter or printer, or a combination of all these devices. That's a brief hardware overview of a digital storage oscilloscope. Unlike a typical analog scope, which is best understood by examining the function of each block, a digital storage oscilloscope is best understood by embracing the concepts behind the hardware. So in this program, we will concentrate on the techniques used to capture, process, and view electrical signals. Fundamental to understanding digital oscilloscopes is the terminology that describes how faithfully signals are captured and reproduced on the scope display. While analog oscilloscopes draw a picture of an input signal using amplifiers that continuously follow every amplitude change in the signal, digital storage oscilloscopes use a process called sampling to take slices or samples of an input signal at specific points in time. The dots you see appearing now show how a DSO would sample the same input signal. In actual practice, these samples would be taken much closer than shown, say 50 to 100 times closer, but the idea is that the samples are taken at very specific times. In a related process called quantizing, an analog-to-digital converter transforms these samples into numbers. These numbers are stored in the DSO's memory in what's called binary format. Both sampling and quantizing are basic processes of digitizing. The faithful reproduction of the input signal by the DSO depends on two key factors: resolution and accuracy. Webster defines resolution as the capability of making distinguishable the different parts of an object, while accuracy is defined as conformity to truth, or to a standard, or to a model. Before accuracy can be obtained, one must have resolution. To show the difference between resolution and accuracy, we'll use this scale, which has a 3-digit readout. When you step on it, the display reads 150 pounds. The register weight could have been anything from about 149 1/2 to about 150 1/2 pounds. So the resolution of this scale is 1 pound, the smallest unit that can be distinguished. But what is the accuracy of the scale? Say we got an official 150-pound weight from the National Bureau of Standards and put it on the scale. Now the readout says 147 pounds, which tells us that the scale's accuracy in this range is 2%, 3 divided by 150 pounds. Both resolution and accuracy are critical in a measurement instrument, whether it's a scale or a scope. How close a DSO's A to D converter output matches the input signal's actual analog value is affected both by the A to D converter resolution and by the quantizing process. The concept of analog to digital converter resolution can be explained using another analogy. Here is a number line with integers dividing the line. If we arbitrarily put points on the line and then ask what number values they represent, we find we are limited to only choosing integers. For points like A and B, which are very close to integer values, that doesn't present too much of a problem. But for point C, the choice is less obvious. Point C is a little more than halfway between 4 and 5. So what number should we assign to C, a 4 or a 5? If we use numbers other than integers, we improve our ability to describe the value of C. Splitting the number line by halves lets us more closely describe the value of C as 4.5. If we split the number line by tenths rather than halves, we would describe point C as closer to 4.6. By adding more numbers to the number line, we essentially increased our ability to describe the value of points on the line. How closely we can describe a point value is essentially the concept of resolution. The analog to digital converter quantizes amplitude values of the input signal at specific points in time. Like the number line analogy, an A to D converter has limited resolution. The amount of vertical resolution depends directly on the number of values it can represent. Digital storage oscilloscopes typically use 6 or 8-bit A to D converters. Some high-resolution DSOs use 10-bit A to D converters. In decimal numbers, this means that 6-bit DSOs can resolve 64 discrete vertical levels, typically specified for 8 divisions. By comparison, 8-bit DSOs can resolve 256 discrete levels, typically specified for 10 divisions. 10-bit DSOs can resolve 1,024 discrete vertical levels, typically specified for 10 divisions. Comparing 6-bit resolution to 8-bit resolution over one division, we find that 6-bit A to D converters distinguish 8 levels per division, while an 8-bit A to D converter distinguishes 25 levels. This drawing illustrates what one division of a waveform would look like on a 6-bit scope. Here's a drawing of the same waveform segment as it would appear on an 8-bit scope. With more levels available, the 8-bit reconstruction is more faithful to the original wave shape, which gives users higher confidence in the measurements. The major limiting factors for vertical accuracy in DSOs are the accuracy and linearity of the analog input amplifier, the A to D converter, and the analog vertical output amplifier. Because these blocks have analog sections, their performance is limited by the analog characteristics of those sections. So DSOs typically have vertical error specifications between 1 and 4%. The major factor affecting horizontal resolution is the record length. Record length is the total number of acquired samples per stored waveform. A DSO may be able to display all or only a part of the total number of samples in the record. For example, a digital scope with a record length of 512 samples may display 512 points horizontally. On the other hand, another DSO with a record length of 4,096 points may only display 1,024 points horizontally. DSOs like this provide some means for viewing different parts of the record. For instance, scrolling. A typical record length for DSOs is between 512 and 4,096 points. Many digital oscilloscopes use both crystal-based clocks and analog ramp generators to produce timing signals for the horizontal time base. Typically, the clock signals are used for the majority of time-based settings. Analog ramps are used in conjunction with the crystal clock for the fastest time-based settings. So the horizontal accuracy of a DSO is determined both by the accuracy of the crystal clock and analog ramp generator, and in some cases, the CRT linearity and accuracy. The accuracy of measurements made on DSOs is greatly improved with digital cursor measurements. Measurement calculations are not made on the displayed waveform, but instead the microprocessor performs these calculations on sample point data stored in the scope memory. As we said earlier, sampling is the process of obtaining the value of an input signal at a specific point in time. There are two major categories of sampling: real-time sampling and equivalent time sampling. In real-time sampling, all sample points for a waveform are obtained in a single pass. Because samples are taken all at one time, the sample rate must be sufficient to collect enough points for faithful reconstruction of the input signal. Digital storage oscilloscopes typically use real-time sampling to capture both single-shot and repetitive signals. Equivalent time sampling allows DSOs to extend scope bandwidth. With repetitive signals, we can use equivalent time sampling to increase the effective sample rate. Equivalent time sampling has two major subsections: synchronous sequential sampling and random sampling. Basic synchronous sequential sampling collects 1 point of information for each acquired signal cycle. Each sample point is referenced in time to the trigger point, thus the name synchronous sampling. This process is repeated until enough points are sampled to fill the memory. For example, if the memory can hold 1,000 points, then it would take 1,000 acquisitions to describe the signal and fill the scope memory. Random equivalent time sampling acquires sample points in a random sequence relative to the trigger point. In this simplified view, only one sample point is taken per input cycle. But many DSOs actually take more than 1 point per input cycle to speed up acquisition time. A DSO's stated sample rate refers to the scope's maximum sample rate. To maintain the same number of displayed points, the actual sample rate of a DSO changes based on the sweep speed setting. At slow sweep speeds, the sample rate is significantly reduced from the scope's stated maximum sample rate. Let's see how this works. We'll assume the DSO has a 1,000-point record, and enough samples will be taken to fill the record. If the time base is set to 1 second per division, the full screen equals 10 seconds. 10 seconds divided by 1,000 points equals 0.01 seconds. This is the time between sample points. The actual sample rate is 1 divided by 0.01, which equals 100 samples per second. The sample rate at this sweep speed would be the same for a DSO specified as a 20 megasamples per second scope or a 100 megasamples per second scope. Compared to the specified sample rates, 100 samples per second is significantly lower. Reduced sample rates at lower sweep speeds can mean a loss of signal detail. Many DSOs have peak detect and envelope features that overcome this limitation. We'll talk about these features later in the program. Aliasing is a term that describes what happens when a DSO digitizes an input signal with an effective sample rate that's too low. The waveform displayed on the DSO may have a much lower frequency than the actual input signal. To reduce the possibility of aliasing, you need to know these items. What are the specific capabilities of the scope you are using? What is the effective sample rate? What are the frequencies in the signal you are measuring? Once you know the answers to these questions, you can determine the appropriate sweep setting for the signal you want to capture. After a waveform has been digitized and stored in the oscilloscope memory, there are several different methods for reconstructing the waveform on the display. All methods require a digital to analog converter to change the digital data back into the familiar analog form. The main job of the D2A converter is to change numerical information into an analog voltage. This voltage, in turn, drives the display circuitry. Seeing what happened before or after a particular signal event occurs can be essential when designing or troubleshooting electronic devices. Sometimes the circuit glitches just before the desired event occurs, causing problems in following circuits. Or the signal's leading edge doesn't have the proper shape or rise time. Or a circuit may take too long to settle after generating one signal event, or begin generating the next signal event too soon. In any of these examples, a digital storage oscilloscope provides the option of viewing the waveform before or after the trigger point. By selecting a pre-trigger display, we can view any events that occur before the start of the signal, and also view all of the leading edge of the signal. For viewing events that happen after a signal event, we can select a post-trigger display. The dot display method uses dots to represent sample points in reconstructing the wave shape. Dots are useful as long as you have a sufficient number of sample points. For instance, these few points provide little pattern indication. But when we add more dots, the wave shape becomes more apparent. Generally, 20 to 25 dots or samples per cycle are required to provide a good display. One of the problems with dot displays is that as the frequency of the input signal increases with respect to the digitizing rate, fewer dots will be available to form the waveform. This can lead to a problem called perceptual aliasing. Perceptual aliasing means that what you see displayed may not be the true picture of what a signal actually looks like. When you look at a series of unconnected dots, you begin seeing familiar patterns in the dots. For example, you might see a pattern in these dots representing several sine waves laid over the top of one another. But in reality, these dots actually represent sample points for a waveform that looks like this. So essentially, perceptual aliasing is an optical illusion. Perceptual aliasing in dot displays is easily corrected by using vectors. Vectors provide a better indication of the wave shape, and we don't need as many sample points to actually show the wave shape. When used for reconstructing sine waves, a vector generator requires only 10 data points per cycle of the sine wave to reconstruct a recognizable display. Vector displays also make glitches more visible by connecting every data point and preventing a single dot, far from the rest of the waveform, from being overlooked. One sine wave reconstruction method uses a circuit called an interpolator. Sine interpolators provide very accurate representations of the original signal, as long as no aliasing occurred when the signal was acquired. And because this type of interpolator is designed specifically for sine waves, an accurate reconstruction can be made with very few data points. A common problem associated with digital storage oscilloscopes is missing signal details that occur between samples. A DSO sample rate is the major limitation in capturing narrow glitches or noise spikes. To guarantee the acquisition of a sample somewhere on the glitch must be wider than the sample interval. If it's narrower, then it probably won't be sampled. As discussed earlier, a typical digital storage oscilloscope uses the specified maximum sampling rate only at the fastest time-based settings. The sample rate decreases significantly at slower time-based settings. In the Tektronix 2230, the peak detect mode avoids missing signal details by always sampling at 10 megasamples per second. This means the 2230 can capture signal details as narrow as 100 nanoseconds. The Tech 2430A uses a different approach to capturing narrow signal detail. The 2430A uses an analog peak detection circuit prior to the A to D converter. This circuit continuously follows the signals between samples. Then peak values are held long enough to be sampled during the next A to D cycle. Using this technique, the 2430A can trap glitches as narrow as 2 nanoseconds and hold them for sampling. For monitoring circuit conditions over long periods of time, the 2230's accumulated peak detect mode simplifies the process. It keeps a running record of all the signal minimums and maximums. Any glitches, amplitude, or timing drifts will be captured and displayed. So the scope can monitor events unattended for minutes or hours, displaying the stored differences for evaluation when you return. Scan is the normal display mode associated with digital scopes. A trigger is received and the scope displays a trace from left to right. Another display format is similar to an electronic chart recorder. This method, known as roll mode, usually is used on slower sweep speeds. This mode disables triggers, so signal data is continuously acquired and displayed. The waveform display scrolls from right to left, across the CRT with the latest samples appearing at the right edge of the CRT. Scan roll scan is a single sweep mode. The scope scans from left to right to the selected pre-trigger point. Then the display rolls right to left. When a trigger occurs, the scope scans the rest of the waveform to fill in the record. Freezing pre-trigger information as well as the waveform allows you to see what caused the scope to trigger. This feature is especially useful for babysitting. You can set up the scope controls to capture a rare event, then do other things while the scope waits for the proper trigger event. When you return, the scope has captured the event plus the pre-trigger information. Although the noise accompanying a signal may be what you want to examine, many times you will only want to examine the characteristics of the signal. A digital scope feature that's useful for separating random noise from signals is average mode. This mode takes incoming signals and averages them over many acquisition cycles. Random noise can be eliminated by taking the difference between the time reference sample points and the random noise. During each acquisition cycle, the scope adds a correction factor based on averages of previous acquisition cycles. The result is a cleaner, more precise representation of the signal. More precise because averaging increases the resolution of the measurement if the average result has more digits of resolution in memory than the A to D converter. In other words, the resolution of the displayed signal can exceed the specified resolution of the A to D converter. For example, when using averaging with an 8-bit A to D converter, the measurement approaches 12 bits of resolution. Quite often it's desirable to store more than one waveform in the scope for later comparison to other waveforms. Most digital scopes have a storage memory, sometimes called a save reference memory, which is separate from the acquisition memory. Waveforms can be transferred to the storage memory and retained for as long as desired. Then a saved waveform can be used for comparison to newly acquired waveforms. For example, the Tektronix 2230 has a 4096-point save reference memory that can store a full 4K record, or alternatively, 3 1K records in 3 individual save reference memories. Any individual memory can be displayed by itself or simultaneously with any or all other waveform memories. The stored waveforms can also be repositioned and expanded or compressed vertically or horizontally. Some digital storage scopes have memory that retains data even when the main power is turned off. This non-volatile memory lets users store waveforms in the scope for long periods of time. For example, the TEC 2230 has an optional 26,000-point non-volatile memory. This allows storage of up to 26 waveforms. An interesting use of this feature is to store waveforms at a remote location and return to a main location to compare the stored waveforms to a known reference. Or standard reference waveforms could be loaded into the scope and taken to the remote site for comparison. One of the most impressive things about digital scopes is the capability to output waveform data to external devices, such as hard copy units and computers. The majority of digital storage scopes available today can transfer waveform data directly to a hard copy device, such as a plotter or printer. A printer or plotter provide large-size printouts of waveforms, which can include the CRT graticule and readout information. These printouts can be used for immediate analysis or for archiving purposes. Once waveform data has been transferred to a computer, three powerful things can happen. The data can be stored in some sort of permanent storage medium, such as magnetic disk. The data can also be manipulated mathematically by any number of software programs. Previously stored, manipulated, or mathematically generated data can be transferred back to the scope. The capability of storing unlimited numbers of waveforms provides a convenient way to build a library of waveforms. By directly transferring the waveform data to the computer, users save the time previously taken up inputting the data by more tedious means. And depending on the software and the computer, hundreds of thousands of calculations can be processed in minutes. Typical hardware interfaces for connecting digital scopes with other devices include the IEEE 488 General Purpose Interface Bus, GPIB for short, and the RS-232C interface. Many Tektronix scopes offer both types of interfaces as options. GPIB interfaces are used primarily when more than one instrument will be controlled, and where the fastest data transfer speed is necessary. Cable length is limited in GPIB systems, so the scope has to be close to the computer. On the other hand, the RS-232C interface allows transfer of data over long distances, so a scope could be remotely located and still be able to transfer data to the computer. By using a modem connected to the RS-232C, waveform data can be transferred over telephone lines. RS-232C interfaces are also used to connect scopes to computers and hard copy units that do not have GPIB interfaces. Digital storage oscilloscopes provide a whole new set of signal processing capabilities. The key to utilizing their full power lies in your grasping the fundamentals of DSO terminology and features. Review material covered in this videotape by actually operating a digital scope. For more detailed information on digital storage, see the primer, An Introduction to Digital Storage.